Assalamu alaikum. Good morning, everybody. Good evening, wherever you are. Today I am going to talk about a new chapter. I am going to talk about eigenvalues and eigenvectors. And this is a very interesting idea here. Let me start by a motivation. Well, if I give you a matrix, and I'm going to take it just 3 by 3 matrix. 1, 2, 3, 4, 5, 6, 0, negative 1, 1. Okay? And I ask you here, find A exponent 2020. So I'm asking you here to multiply this matrix by itself 2020 times. Well, think about how much computation you need to do. And this is just 3 by 3 matrix. You need to multiply A by A, then by A another time, by A another time. So even if you use your calculator or you use your computer, that is a lot of computations here. Okay? Well, what if this matrix is not 3 by 3? What if it is 100 by 100? And we ask you here, find A exponent 1 million. And maybe here you are thinking, well, Professor, why do you want to torture us in this way? Well, actually, this is not out of reality. Actually, this is a real situation that we face when we solve real problems. Let me help you to understand why do we need to understand something like this. Well, let's think here about you are representing something as a sequence or recurrence relation of vectors. So let's say here you have x n plus 1 equals axn. Here n equals 0, 1, 2, and so on and so forth. Here, x is a vector in Rn. Here, this matrix is n by n matrix. And this is a vector in Rn. Well, why do we need something like this? Well, today everybody, or now everybody is talking about the coronavirus. So you can think about, you are representing the current situation of the coronavirus in terms of a vector, and you are modeling the development of this coronavirus, the progress or the spread of this coronavirus. Then you can think about, you are representing this somehow as a vector, and the process is modeled by A multiplied by X. Now, this you can say it's the current generation, and this is the next generation. So this is the progress in modeling the virus. Well, of course here, I mean, this is a naive way of thinking about it. I'm not saying this is exactly what happens. But I'm trying here to make it as simple as possible, the idea. So what happens here, you think about the current representation of the virus as initial vector, and then after the development, you can think about x1. Well, what is x1? x1 is going to be ax0. Then after that, it will be x2, and x2 will be what? It will be ax1, but x1 is ax0, so that is going to be ax0, which is a squared x0. So if you continue in this way, you can think about xn equals an x0. And to understand the progress of this disease, you need here to think about, well, what is A exponent n? Now, n you can think about it as small number, or you can think about it as large number. So you can think about what happens if n here is large, like 1,000, 2,000, 1 million, whatever it is, because that will tell you what happens here in xn, or the progress in your representation of the virus. Well, let's stop here and just think about now how to answer my question about addressing A to some large exponent. Okay? Well, if you think about it in a computational way, I mean, you are wasting your time. Even supercomputers cannot handle this when your matrix is large. Okay? So we have to develop a smart way of handling this. Well, this is how we can think about it. Suppose, or can you find a vector V and a scalar lambda such that A V equals lambda V. Suppose you can do that. Okay? Well, how is this going to help us here? Well, let's think about it. This is a matrix multiplied by this vector equals a scalar multiplied by this vector. Now, what happens if I multiply both sides by A from the left? So A squared V equals A lambda V, and that is lambda AV. But what is AV? AV from this step, it is lambda V. So actually here you get lambda squared V. So A squared V becomes lambda squared V. I multiply by this again by A from the left side. So, and keep doing that. What do you get? You get AN V equals lambda N V. And if you think about this, this is interesting because instead of thinking about A exponent n, you can narrow this down to lambda n multiplied by v. And lambda here is a scalar, so that is very easy to deal with. Okay? So now, in addressing this question, well, the first step is we need to think about something like this. Okay? In particular, we need to think about finding a vector v and a scalar lambda such that AV equals lambda v. Okay? So if we know how to handle this, then this will help us later on to address a question like this one. Okay? So now let me write a formal definition. Let A be an n by n matrix. If a vector V in Rn, and here I should say a non-zero vector, a non-zero vector V in Rn, and a scalar lambda in R that satisfy AV equals lambda V are called the vector, we call it eigenvector, and the scalar, we call it eigenvalue. So what do we mean by an eigenvalue and eigenvector? Well, an eigenvalue is a scalar that satisfies this equation for some non-zero vector v, and the non-zero vector v is called an eigenvector. Okay? So that is what we need. We need now to understand how to find eigenvalues and eigenvectors of a matrix. Well, that is the concept. Now the question is, how do we do the computations and how do we find the eigenvalues and eigenvectors of a given matrix? Well, let's think about it here. When you have AV equals lambda v, we can move this to this side and say here A minus multiplied by v equals the zero vector. Now, minus what? I'm taking v out here. So I'm left with A here, and I'm left with what here? Well, this is a matrix, so this should be lambda I. And I here is the identity matrix, the n by n identity matrix. Okay? So this implies this. So look at this. What do we have here? Here we have a homogeneous linear system. Okay? So V here is a vector I don't know, and this here is a matrix. Okay? So how do you solve this? Well, we know this from chapter 1, and we know everything about it. Okay? So what do we want? We want to have a non-zero V, which means a non-trivial solution for this linear homogeneous system. So in this case, what do we need? We need this matrix to be invertible or non-invertible. We need this matrix to be non-invertible, because if it's invertible, it means the only solution is the trivial solution, correct? All right, so we need this matrix to be non-invertible. Or you can say we need this matrix to have a zero determinant. So basically here, to address my question about finding here lambda and v, you need to think about the determinant of A minus lambda I. You need the determinant to be 0, and from there you get an equation. You need to solve the equation for lambda and see which values of lambda will make this true. Okay? So now we covered the basic idea, and we gave a motivation. Why do we need this? Now it is time to see an example and see how do we do this computationally. Okay? So now let's start by an example. And as usual, I'm going to start with a very easy example. Okay? So let me here take this example. A equals 1, 4, 2, 3. Find all eigenvalues of A to find all eigenvectors of A. All right, so now we need to find the eigenvalues and eigenvectors of A. So what do we need to do? We need to solve determinant A minus lambda I equals 0. So what is determinant A minus lambda I? What is A minus lambda I? Well, this is 1 minus lambda, 4, 2, 3 minus lambda. And you need now the determinant of this. Well, what's the determinant here? It is 1 minus lambda into 3 minus lambda minus 8 equals 0. So what do you get here? You get lambda squared minus 3 lambda minus lambda minus 4 lambda. And here you get plus 3 minus 8 equals 0, which is lambda squared minus 4 lambda minus 5 equals 0. So what you have here, you have a quadratic equation, and you need to find the solutions of this quadratic equation. Well, you can solve it in any way you want. You can factor it if you can, or you can use the quadratic formula if it is not easy to see the factors here. Well, it seems this one is easy, so lambda minus 5 into lambda plus 1 is 0. Is that correct? Double check, please. Negative 5 lambda plus lambda, negative 4 lambda, and here negative 5 times 1, negative 5. So from here, you see that lambda 1 is negative 1, and lambda 2 is 5. So you get two distinct solutions here, negative 1 and 5. Those are the eigenvalues of our matrix. Okay? So finding the eigenvalues is straightforward. All you need is to find this determinant and solve, and you get the eigenvalues. Now the question is, how do we find the eigenvectors? Well, you need to take each eigenvalue and go back to the homogeneous linear system and see what is the solution of that. So this is how we do. We start with lambda 1 equals negative 1. Okay? When we substitute, we get A minus minus 1, that is a plus 1, I into V equals 0. And that means what? It means 1 plus 1, 2, 4, and here 2, and here 3 minus negative 1, that is 4. Now, V, I don't know what is V. So far, I don't know what is V. So let's take it x1, x2 equals 0, 0. So this is our linear homogeneous system. So we need to find x1 and x2, and all of you know that from chapter 1. Okay, so let's solve this and see what we get. Well, this is here 2 by 2 matrix, so you can do here reduced row echelon form, but actually it is easy to solve right away. 2, 4, 2, 4. So what you get here is x1 plus 2 x2 equals 0, and the second equation the same you get. So here you have x2 is free, x2 is free, so let's take a t, and x1 is negative 2t. So what are we getting here? We are getting here the solution of this homogeneous system. That will give us the eigenvectors that belong to this eigenvalue. So we know this is actually a subspace. Okay? So we write it as follows. E lambda equals negative 1. And that is going to be all vectors of this form. Negative 2t, here t, such that t belongs to R. And that is t into negative 2, 1, such that t belongs to R. This, we call it the eigenspace that belongs to this value of lambda. So this is called the eigenspace. The eigenspace that belongs to lambda equals -1. Okay? So you can see here, it is not only one eigenvector you find. You find an eigenspace. You find a space of eigenvectors. Okay? However, we know this eigenspace is spanned by this vector. Okay? So here it is common to say v equals -2, 1 is an eigenvector. An eigenvector of A. So basically here, you take the vectors in your bases and you consider them as your eigenvectors, because everything else is going to be spanned by the vectors in your bases. Okay? So this is the first eigenvalue, and here we found the corresponding eigenvector. Okay? Now, let's take the second eigenvalue. Well, it will be similar. So here, lambda 2 equals 5. You have A minus 5I into V equals 0. And what is this? This is going to be 1 minus 5 is -4. Here 4. Here 2. 3 minus 5 is -2. And here, we don't know what is V, so you set it x1 equals x1, x2, and here 0, 0. So now you solve. Again, when you solve, you get x2 is free, x2 is free, and you get x1 equals x2. Am I correct? All right. So here, the eigenspace that belongs to lambda equals 5 is T and here T, such that T belongs to R. And that is span of what? Span of this vector. 1, 1. So here is the eigenspace, and we know a basis for this eigenspace. So now we can say the eigenvector, or 1, 1, is an eigenvector. V equals 1, 1 is an eigenvector that belongs to lambda equals 5. So here we found all eigenvalues and all eigenvectors of this matrix A. Now, there is one thing here I want to stress, and later on we are going to come back to this. What is the dimension of this eigenspace? Well, obviously the dimension is 1. What is the dimension of this eigenspace? The dimension is 1. So here dimension 1, here dimension 1, 1 plus 1 is 2. How many eigenvalues we got here? 2. So keep that in mind. We're going to visit this idea again and establish interesting relationships here. Okay? Well, we can write some facts that are easy to conclude from this. The first fact, if you have an eigenvector, then any scalar multiple is also an eigenvector. So let me write that. Fact number 1, let A be an n by n matrix. If V is an eigenvector, then KV is also an eigenvector. That is very easy to observe, because when you find an eigenvector, the span of that is also in the eigenspace. So any vector in the span of your vector is going to be an eigenvector. If you want to prove it here, you can prove it as follows. Let lambda be an eigenvalue of A and V be an eigenvector. So you have AV equals lambda V. So what happens now if you multiply this by K from here and this by K from here? Now you invite the K in, so this will be a KV equals lambda KV. So basically, whenever you have an eigenvector, any scalar multiple of that is also an eigenvector. So that's easy to observe from this example, and it's easy to prove in general. Okay? Fact number 2. Fact number 2. If lambda is an eigenvalue of A, then lambda to the n is an eigenvalue of A to the n. Why is that? Well, let's think about it. Lambda is an eigenvalue, so you have an eigenvector, and here AV equals lambda V. So this is the eigenvalue that you have, and this is an eigenvector belongs to this eigenvalue. So now if I multiply by A, I get A squared V equals lambda AV, and that is lambda squared V. So you have A squared equals lambda squared V. Keep going in, here there is V. So keep going in this way. What do you get? You get A n V equals lambda n V. So when you have an eigenvalue, lambda of a matrix A, then lambda to the n is going to be an eigenvalue of A to the n. And that's very easy to observe in general. Okay? All right. So now we are ready for a second example. Example 2. Okay, let me take this example. 1, 2, 3. A is 1, 2, 3. 0, 1, 4. 0, 0, 5. By the way, in this fact here, when I said lambda is an eigenvalue implies lambda to the n is an eigenvalue, I can ask you, well, what happens about the eigenvector? What happens to this? Look here. What happens to this? Well, this stays the same here. So I can twist this fact and create a new fact saying that if V is an eigenvector of A, then V is also an eigenvector of A to the n. Okay? And that follows from the same argument here. Okay? So I can twist this fact number 2 and make it a new fact about the eigenvectors of A. Relate them with the eigenvectors of A to the n. Keep that in your mind. All right. So here we have a matrix. This matrix is a 3 by 3 matrix. And now, again, we want to ask the same questions. Find all eigenvalues and find all eigenvectors. Well, what you need to do here, find all eigenvalues and eigenvectors. What you need is determinant A minus lambda I. What is that? That is determinant of 1 minus lambda, 2, 3, 0, 1 minus lambda, 4, 0, 0, 5 minus lambda. Am I correct? Double check, please. A minus lambda I. That's what you get. And what is this? This is a triangular matrix. We know what is the determinant right away. This is going to be 1 minus lambda into 1 minus lambda into 5 minus lambda. Correct? And here you can see the eigenvalues. You can see lambda 1 equals 1, and that is repeated twice. And you can see lambda 2 is 5. Okay? So now, before I go further, I want to stress something. This matrix is a triangular matrix. Now, look at the eigenvalues. 1, 1, 5. What are those? So, can we make this a general rule? If we have a triangular matrix, then the eigenvalues are going to be the elements along the diagonal. Correct? Here it is. And that is easy to prove in general, not only in this example. So if you have a triangular matrix, then the eigenvalues are going to be the elements along the diagonal. And that's very easy. You don't need to do all this work. So from now on, if you have a triangular matrix, right away you see the eigenvalues. Okay? Keep it in mind. All right. Now, we have also something interesting here. We have an eigenvalue that is repeated twice. Okay? So we call this the multiplicity of the eigenvalue. Okay? When you have an eigenvalue that is repeated, we call that the algebraic multiplicity of the eigenvalue. So this eigenvalue 1 repeated twice, this eigenvalue 5. All right. So let's find now the eigenvectors. So we take lambda 1 equals 1. And what do? We solve this homogeneous system. A minus 1 I into V equals 0, which is going to be 1 minus 1, 0. That will be 2, that will be 3, 0, 0, 4, 0, 0, 5 minus 1, 4, multiplied by x1, x2, x3 equals 0, 0, 0. Again, that's very easy to solve here. So what do you get? Well, if you think about this, it's actually in echelon form. So here, from here, you can say 4x3 is 0. So that means x3 is 0. Now you go upstairs here, and you get 4x2, 0. This means that is here you get also 4x3 equals 0, so you get nothing here. Now you go here, and here you get 2x2 plus 3x3 is 0. So what are we getting here? We are getting here x3 0, so x2 is 0, and in that case x1 is free. Am I correct? Double check, please. From here, we get x3 equals 0. And from here, we get again x3 equals 0. And from here, we get 2x2 plus 3x3 equals 0. But x3 is 0, so x2 is 0. So we are left with x1. It is free. OK, so what are we getting here? We are getting the eigenspace that belongs to this lambda is x1 free, so let's take it here t, and x2 is 0, x3 is 0, such that t belongs to R. And that is a span of 1, 0, 0. So we got here the eigenspace that belongs to this lambda, and it has dimension 1. Okay? Now, you can say this is your eigenvector. Hence, this vector v equals 1, 0, 0 is an eigenvector of that belongs to this lambda. All right. Now, we do the same thing for the second lambda, lambda 2. Lambda 2 equals 5. And since it's similar, I'll leave it for you, but let me write down here what we get. We have a minus 5I, v equals 0. And in this case, what you get? You get negative 4, 2, 3, here 0, here negative 4, here 4, 0, 0, and here 5 minus 5, that is 0. And here x1, x2, x3 is 0, 0, 0. Now you solve and you find here E, the eigenspace that belongs to lambda equals 5. And I'll leave it for you here to write it. So basically that's again simple here. So from here you get negative 4x2 plus 4x3. So x2 equals x3. So here I can say here t and here t. And from here you get negative 4x1, negative 4x1 plus 2x2 plus 3x3 equals 0. So negative 4x1 is going to be negative 2x2 minus 3x3, and x1 is going to be negative 5t over negative 4. So this is 5 over 4 t, such that t belongs to R. Double check that, and I'll leave it for you to finish the details here. Okay, so for this matrix that I started with, we found all eigenvalues and all eigenvectors here. All right, we have more interesting facts we can talk about here. And the first one is very, very important fact. This was, I think, fact number 4 or 5. So let me write it. Fact here. Let A be an n by n matrix, and lambda 1, lambda 2, lambda n be eigenvalues. Now, why did I say lambda 1 to lambda n? Why didn't I say lambda 1 to lambda k, for example? Well, if you go back to the way we found the eigenvalues, it's determinant A minus lambda I equals 0. And the determinant of n by n matrix here, when you do this, you get a characteristic equation. The characteristic equation here is actually an nth degree polynomial in general. So you want to solve or find the roots of nth degree polynomial, so that will give you nth root, actually. It's by the fundamental theorem of linear algebra, which is something we don't talk about in this course, but in general, when you have n by n matrix and you find the characteristic equation and you solve, you get n roots, okay? Of course, some of them can be repeated, some of them could be complex, as you know, when you solve a quadratic equation. It's possible that you get complex roots, okay? So whatever they are, whether they are real or complex, whether they are repeated or not, let's say we have lambda 1, lambda 2, lambda n, okay? Here is the interesting fact. One determinant of A is the product of those eigenvalues. Now, if you go back to the examples that I gave you, multiply the eigenvalues, you will find that is exactly the determinant of your matrix. Fact number 2, the trace of your matrix is the sum of the eigenvalues. And that's very interesting. Very simple and very interesting. Okay? So when you find the eigenvalues, an easy way to check whether you did it correct or not, just add them and add the trace and see. Okay? That is a nice way to check whether what you did is correct or not. I'm going to prove the first one, because the first one is very easy to prove. The second one, just take my word for that. Okay? At the time being. So let's prove number 1 here. Proof of 1. Well, you need this, determinant of A minus lambda I. Okay? And as I said, you find the determinant in whatever way you want. You are going to find the characteristic equation, and now you factor it. Well, I'm writing A minus lambda I, so we can expect here lambda minus lambda 1 into lambda minus lambda 2 into lambda minus lambda 3, and you keep going lambda minus lambda n. Now, because here I have minus lambda, and here I wrote them lambda minus lambda 1, so here I have negative 1 exponent n. Correct? Now, don't tell me how did you factor that. Well, suppose in a magical way we factored the characteristic equation in this way. Okay? So that is what you get. Each factor will give you an eigenvalue. Okay? Well, now let's think about it. What happens when lambda is 0? If I take this to be 0. On this side, we get determinant of A. And on this side, what do you get? Well, you get here negative, negative, negative. That is negative 1 exponent n. And here you have negative 1 exponent n. So that will cancel out. And you end up with lambda 1 multiplied by lambda 2 multiplied by lambda 3 up to lambda n. So that is exactly what we are talking about. The determinant of A is the product of the eigenvalues. Okay? And that is very simple, very interesting. Okay? Now, look at this. What happens if one of the eigenvalues is 0? If one of them is 0, what happens to this? Well, you get 0 here. What does that mean? The determinant is 0. What does that mean for the matrix? If the determinant of the matrix is 0, then your matrix is invertible or non-invertible? Then your matrix is non-invertible. Okay? So from this fact, you can write another easy fact. So here is another easy fact. If one of the eigenvalues of A is 0, then A is non-invertible. Okay? If one of the eigenvalues of A is 0, then A is non-invertible. And you can see it right away from here, so I don't need to write another proof for that. Okay? All right. We can write another fact here. Suppose none of the eigenvalues is 0. It means, actually this here I said if one of the eigenvalues of A is 0, I can make it both ways. I can write it if and only if. So one of the eigenvalues of A is 0 if and only if A is non-invertible. So if it is non-invertible, then one of the eigenvalues of A is 0. And if one of the eigenvalues of A is 0, then it is non-invertible. So it goes both ways. Okay? Suppose your matrix is invertible. So it means none of the eigenvalues is 0. Suppose A is invertible. So none of the eigenvalues, based on this fact, none of the eigenvalues is 0. Okay? Now, let A be an eigenvalue of, let lambda be an eigenvalue of A. So this means A V equals lambda V for some eigenvector V of A. Now, A is invertible. This means A inverse AV equals A inverse lambda V. Now, this means identity times V is lambda A inverse V. Now, divide by lambda. Lambda is not 0 because A is invertible. So this means A inverse V is 1 over lambda V. So from here, what can you say? Let lambda be an eigenvalue of A is invertible. What do we get? We get 1 over lambda is an eigenvalue of A inverse. So here, the conclusion, then 1 over lambda is an eigenvalue of A inverse. And here we can ask you an easy but actually challenging question. We give you a matrix and we ask you find the eigenvalues of A inverse. In this case, you don't need to find A inverse. All you need is to find the eigenvalues of A. Okay? And if none of them is 0, then your matrix is invertible, and in that case, the eigenvalues of A inverse are going to be the reciprocals of the eigenvalues of A. So that's very easy fact, but it can help you to address certain questions. Okay? Basically, that's all in this section. I can give you one final exercise, and I will not do it. I will just write it and ask you to do it yourself as an exercise. Later on, we can use it, but in that case, you need to give me the answer. Okay? So here is the last example. Consider A equals, I'm going to take 3 by 3 matrix here, 6, 3, 6, 3, negative 8, 0, negative 2, 0, 1, 0, negative 3. And again, I'm going to ask, find all eigenvalues of A to find all eigenspaces of A. Find the eigenvalues of A and find the eigenspaces of A. And I'll leave it for you as an exercise to do it. So when we use this matrix right away, you have to tell me the eigenvalues and the eigenspaces of A. And keep in mind, when you find the eigenspace, you need to find a basis for each eigenspace. Okay? So in particular, you need to know the dimension of each eigenspace. Okay? All right, that's it for today. I'll stop here. I am done with this section. Thank you, and see you in the coming section.